Okay, good morning. This is Unit 8, Day 2. We're going to talk about the P-series test and the integral test for convergence. So remember, our goal is to be able to look at a summation, and we're trying to determine if that sum of numbers created by this a sub n here is going to converge or diverge. So last class, we looked at the divergence test and also at infinite geometric series, and those were the only two we examined. So today we're going to take a look at if that a sub n has this kind of look to it, this 1 over n raised to the p. So our p-series test says that if you're taking the sum from n equals 1 to infinity of 1 over n to some power, that if that power is greater than 1, that summation, that series, is going to converge. And if that exponent is between 0 and 1 including 1, that it is going to diverge. So, if we were taking a look at something like example 1 here, notice that if this was last class and we tried to do the divergence test here, so this is not p-series, if we tried to do the divergence test here, the divergence test says what happens as the limit as n approaches infinity. So if you plug in here, n equals infinity, you get 1 over infinity. Notice that the limit as n approaches infinity is 0. So that tells us that the divergence test is inconclusive and we have to use another test. So we might as well try this p-series test here. So basically, if you wanted to if you weren't sure, maybe you still thought it was geometric or something, you can still kind of generate that list of numbers to kind of see what's going on. Okay, so remember, just to practice generating that series, you start by plugging in this bottom number 1, you plug it in, so you get 1 over 1 squared, which is 1, plus, so that we would call that a sub 1, the first term. Then a sub 2, what you get when you plug in n equals 2, so you would get 1/4 there, because 2 squared is 4, okay, plus, and then you'd get 1/9, and so on and so forth, so plus dot dot dot. We're trying to determine if this series of numbers, if that adds up to something or if it diverges. So when I look at this, I say, well, this does have that p-series look to it. I notice here that this is a p-series with p equals 2, right? So we'll call this p-series with p equals 2, okay? And what can you tell me about 2? Well, it's definitely bigger than 1. So we can conclude that this converges, right? Because if p is greater than 1, then it converges by p-series test. Remember, it's important on the AP exam to state the test that you use in order to get full credit. So converges by p-series test. And then you'd be done there. Okay? And again, the divergence test here would be inconclusive. So then you might say, well, if the divergence test is inconclusive, is it always going to converge? And that's why I want to talk about this example. So, again, if you needed to kind of generate that series of numbers, you could, but I would probably maybe just rewrite this as the summation from 1 to infinity, okay? And I would write that as 1 over n to the 1/3 power, because now I look and I see that this is indeed a p-series. This is a p-series, okay? This time my p equals 1/3. And what can you tell me about 1/3? Well, it's less than 1. See where here 2 was greater than 1, the p was bigger than 1, so it converged. Here, p value is less than 1, therefore diverges by p-series test. Okay, so we can say that that diverges. So again, this is a great example where if you actually did the divergence test, if you took the limit as n approached infinity, you would still get 0. So just because the divergence test is inconclusive does not mean that it doesn't diverge. It just means we don't know. It could do either one. So these are both really good examples of a case where the divergence test is inconclusive, so you need to use another test. So that converges by p-series test. Okay, so pretty simple there. And again, we can just kind of take a look at here. Again, this is a p-series here. P equals 5 over 4. Okay, 5 over 4 is greater than 1. So this is going to converge by p-series. And again, if you're not sure, if you want to go ahead and, you can even use your calculator, just kind of generate out the series of numbers and add them all together, you'll notice that it's going to converge to a number, okay? All right, so converges by p-series. Again, it might be worth it on this one to take a moment to rewrite it so that you can clearly see what the p-value is. So here, I'd say this is the same thing as 2 over n to the 1/2 power. So here, this is a p-series, and p equals 1/2. And so what can you tell me about 1/2? 1/2 is less than 1. So again, I kind of go up here. Okay, 1/2. That means this thing is diverging by p-series test. By p-series. Okay? So that's pretty simple. The p-series test is a nice one. Unfortunately, not all things are kind of going to be, of that form. So we'll take a look at the second page. Okay. So I know everyone's favorite was the improper integrals, and so the integral test is going to kind of use our knowledge of that. So the integral test, it's going to be another one on your pink sheet. It says that for x's that are greater than or equal to 1, and you have to meet the conditions before you can use this test. So it has to be positive, continuous, and decreasing. And basically it says, I do what my friends do, right? So it says that if you have this summation here, okay, and the integral, the improper integral there, if either converges, so does the other. So if you can show me that this converges, then the summation also converges. If you can show me that this improper integral diverges, then so does the summation. So I kind of call this the integral test is the I do what my friends do test. So we're going to kind of use our knowledge with the improper integrals to go from there. So we'll kind of scooch down and do a couple examples. Okay, so I do what my friends do. So on this example, again, you're kind of going through all your tests. If we're trying to determine if this summation converges or diverges, I'm kind of asking myself, is it geometric? No, it's not a p-series, right? So I need to kind of think of another test. So if it looks like something you can integrate, then integrate it and integrate it from 1 to infinity, and then if you can conclude that the integral converges or diverges, then you know what the summation does as well. So you just need to make sure it meets these conditions. Is it continuous, positive, and decreasing? So when I take a look at this, that's going to be continuous. I know some of you are thinking like, oh, what about at negative 4/3? Well, notice that I start by plugging in n equals 1. So this is going to be continuous from 1 to infinity. So continuous, I'll say check. Is it positive? If I'm plugging in all positive numbers there, I'm going to be getting all positives back. So it's continuous, it's positive. And is it decreasing? As n gets bigger here, the magnitude of the overall, each term in the summation is going to be decreasing. So I'm good there. Since it meets all those conditions, I'm going to go ahead and I want to examine the integral of a sub n. So that's kind of that junk there. So I'm going to take a look at the integral from 1 to infinity, okay, of 1 over 3x plus 4. And I'm using an x there because now this is a sub n. I want to integrate with respect to x here. So I'm just using this so that I realize it's, I'm just kind of seeing what this does. And of course, I'm integrating with respect to x. Okay, so we know how to deal with improper integrals. And I'm going to kind of do this the long way. And some of you are going to be using some shorthand when you're going through this, but I'm going to go ahead and do it the proper way. So we're taking a look at this, and we're saying that that's going to be equal. Since this is an improper integral, I'm going to take the limit as a approaches infinity, okay, and I'm going to integrate from 1 to a of that thing, okay? So now I've kind of eliminated the improperness of it by, examining the limit as we approach it, dx there. So now I'm like, okay, now I just need to integrate this. Well, that looks like a u substitution to me, so I hope I don't go into this side too much. But I'm going to go ahead and say u is going to be 3x plus 4. So that means the derivative of u with respect to x, du dx, is going to be 3. Multiply both sides so you get 3 dx. Notice how I really wanted it to be a 1 dx. I have this 3 there, so I need to say, well, 1/3 du equals dx. All right, and don't forget to adjust your limits. So my new limits, okay, it was at 1. Now when I plug 1 into u, I get 7. And it was a. When I plug a into there, I get 3a plus 4. So now I can say that this is equal. Notice I didn't do anything with this limit. I'm going to take that 1/3 and pop it way out. So I'm going to say 1/3 the limit. If it makes you feel better, you could put the 1/3 over here. It doesn't matter. The limit as a goes to infinity. And now I'm going to be integrating from 7 to 3a plus 4. And I'm going to integrate 1 over u du. So that looks much better to me. Okay, so now I know how to integrate 1 over u, right? Normally this is where you'd add 1 to the exponent, divide by that number, but that means I'd get 0, Oh yes, I remember. To integrate 1 over u, you just get ln absolute value of u. So I've still got this 1/3, right? I haven't taken the limit or anything, so this part kind of comes down. So you just rewrite this as a goes to infinity. Now I am integrating this, so that's going to give me ln absolute value of u, okay? And we're going to evaluate that from 7 to 3a plus 4. I can kind of squeeze that in there. Okay, now it's your fundamental theorem of calculus. So we apply fundamental theorem of calculus, and this just comes down. I haven't evaluated the limit yet. Oh, how about I write so you can see it? Let's see here. Sorry. So I haven't evaluated the limit, so I'm still just carrying that down. And my fundamental theorem says I plug this in, so I'm going to do ln 3a plus 4. I don't really need to worry about the absolute value there because we got all positives. You could put it there if you want. Minus what I get when I plug in 7. Absolute value of 7 is still 7. So I get to something like here. Now I'm evaluating the limit. So it's going to be 1/3 times, if I plug in, right, infinity there, I'm going to get infinity times 3 plus 4, which is infinity. So the ln of infinity, well, that's infinity, and then minus the ln of 7. And right there, you kind of, some of you may have even seen a little earlier, this thing is trashed right away because this piece here is diverging, okay? So even if you went through with your 1/3 or whatever, it's not really going to matter because this whole thing diverges, okay? So this, you could say, equals infinity. So now be careful how you word this here. You have to be really careful. So this tells me that the integral diverges, okay? So I'm going to say diverges here. So my conclusion, okay, by the integral test is that the integral from 1 to infinity of 1 over 3x plus 4 dx diverges, okay? So the summation, okay, so the summation as n goes to 1, or n at 1 to infinity of 1 over 3n plus 4 also diverges by, make sure you say your test, so this is by the integral test. I spelled that wrong, sorry. By the integral test. Perfect. Okay? So you've got there. Again, the integral test is kind of, I do what my friends do. So if you can show me that the integral diverges, then the summation also diverges there. And then we can take a look at something a little easier. So over here, what's nice about this one is you can actually do this by p-series test. So very, very quickly you can say, oh, well, this is a p-series. Here, p is 3. We know that in a p-series, if your p-value is greater than 1, right, you can make your conclusion that way. So we know this thing is going to converge, right, by p-series test. But let's just take a look and say you used the integral test, okay? It would be much faster to use p-series, but I just want to practice using the integral test, so I'm going to do it that way. So again, I kind of check these off for myself. Is that continuous? Yeah, because 0 would make this discontinuous, but I'm starting by plugging in 1. So yes, it's continuous. Is it positive? If I start plugging in 1, 2, 3, 4, I'm getting all positive things. So yes, it's positive. Is it decreasing? Well, the magnitude overall of each piece is decreasing, right? Because as I start plugging in bigger numbers for n, the denominator is getting bigger, so this is overall decreasing in magnitude. Okay, so now that I've met my conditions, I say, okay, so now I need to say, well, what test am I going to use? Obviously, you would really use p-series, but since we're practicing the integral test, we're going to do that. So I'm interested in what the integral from 1 to infinity of 1 over x cubed dx is. Okay, that's what I'm interested in. So I know that I can rewrite that, right? That's going to be the integral from 1 to infinity of x to the negative 3 dx, okay? And now you could go through all this limit business, right? But since I'm trying to kind of work quickly through these tests, really we're going to kind of do a cheat move here. We're going to apply the fundamental theorem of calculus with the infinity. We're going to kind of plug that in. So watch how this little move works here. So I'm going to say, all right, I know that I'm going to take the limit as we approach infinity. That's how I'm supposed to do it. But I'm going to kind of use some shorthand. I'm going to say, all right, add 1 to the exponent, divide by that number. And I know I'm not allowed to plug in infinity in my fundamental theorem because it's a concept. But since I'm just trying to kind of prove a point here of convergence or divergence, I'm going to kind of cheat and do it anyways. I don't like this negative exponent, so I'm going to say that's equivalent to negative 1 over 2x squared. Okay? And then I'm going to apply my fundamental theorem. I'm kind of cheating here because I'm using the infinity because I'm really just concerned to see if this converges or diverges. So I'm going to say, well, if I had infinity squared there minus what I get when I plug in 1, watch those negatives. Yeah, 1 squared is still that, so you get something like this. Okay? Well, a number divided by infinity, right? A number divided by infinity, so you have negative 1 over infinity, basically, plus a half. Well, this, a number divided by infinity, is 0 plus a half. So this is 1/2. So we would say that this integral converges to a half. And again, the integral test says that if the integral converges, then the summation also converges. And again, so this, you can see how much less cumbersome it is. I'm still kind of doing the same thing. This is kind of a cheap move here. I'm really not supposed to be applying my fundamental theorem of calculus with an infinity, but we're kind of doing it just because we're really interested to see what this does. If this was a free response or something, I would still probably write it out with all that limit notation, because that's the proper way to do it. So, okay, what am I concluding here? So, I know now that this converges. And when I say this, you have to be careful. So I know that this integral converges. But because the integral converges, I can also conclude that the summation converges. So, since, okay, so we're saying since the integral from 1 to infinity of, x to the negative 3 dx converges, we're going to conclude that the summation of 1 over n cubed from 1 to infinity also converges by the integral test. And I'm running out of space here, but I'm just going to say by the integral test, okay? You've got the idea there, okay? So, and again, we really would have done this one by p-series, but we're just going to do it by integral to practice. Another thing that's interesting with the series is that we can determine sometimes what the series converges to. Like, what number does it converge to? Sometimes we can, sometimes we can just get a range. So using the integral test, we can find an upper and lower bound to a series. So we might not know exactly what number that the series is converging to, but we can give a range. And so the upper and lower bound using the integral test kind of works like this. What you're going to do is, first, if you have to figure out that it converges, right? So by the integral test, if you find that something converges, then you can actually give a range of the number that it converges to. And that range is whatever the integral converges to. So I think in that previous example, we got 1/2. So we know that the summation then will converge to a number between 1/2, so whatever you got, and whatever you got plus plus the first term of this. So you'd actually have to go ahead and generate the first term of this plus whatever that converges, and that gives you a range. So something that's interesting then is that just because the integral converges to a half, say, that does not mean that the summation converges to a half. It's going to converge to something between 1/2 and whatever 1/2 is plus the first term. Okay, so that's interesting, and we can kind of get a range. We might not be able to nail down the exact number, but we can get a range for what it converges to. So we'll take a look at a couple examples of that. So I'm going to go ahead and go back to that example we worked with on the first page. So you might say, why would you ever want to use the integral test on that when we could have just concluded that that converged by p-series? Well, the cool thing about p-series is that it's really quick. You can look at something pretty quickly and say, oh yeah, that converges. But what if they ask you, what does it converge to? So that's why the integral test is a lot more powerful. So yeah, it's easy to conclude here that by p-series this converges, but that's the limitation of the p-series test. You have no idea what it converges to. So by integral test, again, we already established from the other page that this was continuous, positive, and decreasing, right? And we saw that the integral converged to a half. So you can flip back if you need to, but we said that that was a half. So what does this mean for what does the summation converge to? So we can say that the summation is going to converge, and it's going to converge to, well, whatever this is, you just put there, and then that's the lower bound, okay? And then you need to get the first term. So to get the first term, you plug in that bottom number. So when I plug in 1 there, you get 1 over 1 cubed, which is just 1. So basically what we can conclude is that this summation does converge, and that it converges to a number between 1/2 and 1/2. So that's why the integral test is a bit more powerful, because it kind of, not only will it tell you if it converges or diverges, it'll let you kind of get an idea of what it converges to. Okay? So very similarly, this is another example, and I'm just going to kind of walk through it. I know it's already written on there, but I'm just going to walk through it. And sorry about that. Okay, so on this one, this is a new problem. Again, before you can use the integral test, you would want to confirm that it's continuous, positive, and decreasing. You may want to take a moment and rewrite this, right, as 2 over n squared. You can kind of see there. Again, we could tell pretty quickly that this converges by p-series. But what if the test question says, you know, use the integral test to find an upper and lower bound? Obviously, if it is multiple choice, you are just going to, if it just says converge or diverge, you would use a p-series here. But since we want to know more information, we are going to go ahead and do the integral test. So the integral test says I do what my friends do. So I'm trying to figure out information about this summation converging or diverging, so I'm going to look at the integral. So if we integrate from 1 to infinity of 2 to the x to the negative 2 dx, right? And again, I'm kind of using my cheater step here. I know I really should be using that limit notation because I'm not really allowed to use my fundamental theorem of calculus with infinity because it's a concept, but we're just kind of trying to see what this ends up to be. So add 1 to the exponent, divide by that number. There's my fundamental theorem of calculus. Oh, I clean it up, right? Negative exponent, pop that into the denominator. And then here's my fundamental theorem. So I plug in, right, infinity, even though I'm not supposed to, but I'm going to anyways. So I plug that in to get an idea of what's going on here, minus what you get when you plug in 1. So I get this. Negative 2 divided by infinity is 0, and that turns to a plus 2. So here I can conclude that the integral converges to 2. That does not mean the summation converges to 2. It's just enough to tell me that the summation converges. That does tell me the lower bound. So if I want to find the lower bound, or the bounds of what this summation converges to, I take this 2, and I say that this summation, the thing I was trying to do, it's going to converge to somewhere between 2 and, to get the upper bound, you just have to find the first term. So the first term you get by plugging in n equals 1 into there. So if you plug in n equals 1, it might be easier to see if you look up here. So if you plug in n equals 1, you get 2 over 1 squared, which is 2. So that's where this 2 came from. So it's your first term, 2, plus what the lower bound is, 2. They just happen to both be 2 there. So I could tell you that this converges to some number between 2 and 4, okay? And it didn't ask me if it can converge or diverge, but I didn't make a concluding statement there, but you kind of get the idea. Okay? So there you have the P-series test, integral test, and finding the bounds of convergence for a summation. Have a great day.